PhD student, computer science in Northern Illinois University. Today I'll be talking about something about large language models and what is the large language model, why you are using large language model, and what type of works and how we can use appropriately large language models. And later I will describe about what type of problems exist in large language models and how we can overcome these problems. Yeah, so this is the introduction. We know that generative AI, so large language model is one type of generative AI. It can generate various type of contents like text, image, audio, video, or various type of things based on the training data. Large language model trained on the large corpus of data, and it can generate those type of things. The popular large language model is GPT, GPT-4, DALI, Stable Diffusion, ChatGPT. So the importance is large language model or generative AI can be useful for industries, healthcare, education, or entertainment, or various purposes. So a large language model is a deep learning model trained on a massive text dataset to understand, generate, and process human language like GPT-4, Llama 3, BART, T5, etc. So how it works? It uses deep neural networks, particularly transformers, and in the transformers, it will work. Attention mechanism works here. It pretends on vast amounts of text using self-supervised learning, and it can be fine-tuned for specific tasks, something like healthcare or education or politics or something like that. Applications basically transformer built on the attention mechanism, and attention mechanism actually worked on for machine translation, something like like English to French or something, speech conversation. It can be useful for text summarization, code generation, or conversation AI. So there are some challenges. The first challenges is high computational cost, because for the large language models we have to use such big number of transformer model, and which is a little bit computational costly. And there are some bias and ethical consideration. And another problem is context length limitation. It is for each LLM there are some input constraints, like such type of tokens we can use for input. So this is the context length limitation of large language models. So there are some important things we can use in large language models. Like for flexible adaptation, we can use zero-shot learning, few-shot learning, or in-context learning. For the reasoning things, we can use large language models in chain of thoughts, tree of thoughts, or graph of thoughts. We can do fine-tuning or prompt tuning for improve the large language model performance, and we can use flash attention mechanism inside the large language model to improve the efficiency of LLM. So at first, I'm describing about in-context learning. So what is in-context learning? In-context learning is we don't update the model weights. It should be still same. We will do something in prompt. Like we will teach large language model inside the prompt, not the model weights. So we'll do some few examples, which is called few-shot learning, or we don't need to do any examples. Just ask some question. This is called zero-shot learning. So there are some pros and cons of in-context learning. First is pros is we don't need to do fine-tuning. It's adaptive for different tasks. Fine-tuning is costly. We don't need to do fine-tuning. The cons is there are some memory limitations on input length. So for each LLM, there are some context window size. Suppose like GPT 3.5 have 16K token limit, Llama has 16K token limit. So there are some input token size limit. So this is the limitations for in-context learning. So what is zero-shot learning? Zero-shot learning is it's a model makes predictions on tasks it has never seen before. So it's like just a question about something, what is the capital of United States or something like that. Like just a question, or you want to do whatever you want, but you are not providing any examples or anything. So you are not training the model, you are just asking any particular question, and LLM will respond based on this, based on his previous knowledge. So the pros is you don't need to use any table level data or anything, but the cons is oftenly zero-shot learning performs lower than other type of approaches. So now, what is few-shot learning? So few-shot learning is zero-shot learning is we are not providing any examples, but few-shot learning is we are providing some examples like 2 or 5 examples, and then we are asking some questions, and in this based on this example, LLM will respond something like that. So this is the few-shot learning. The process same thing. We don't need to fine tuning. This is little bit computationally inexpensive, but the cons is sometimes it depends on the examples. If the examples is not good, then LLM performs like LLM does not perform well. Now there is another part in large language model. It's called reasoning. So there are two things. One is regular LLM. So here we are asking some question, and large language model generates some answer. Suppose like it can be either few shot or zero shot, anything. This is called regular LLMs. And what is reasoning LLMs? Reasoning means large language model thinking little bit deeply. So there is a question, and then for the reasoning for large language model, there should be multiple thought process, and then there is an answer. So based on this thought process, large language model performs a little bit better based on this regular one. So there are two type of things in reasoning. First one is it's just a question, what is 3 plus 2, and then large language model says that, okay, the answer is 5. But here there are 3 type of reasoning. The first one is just it will generate a 1 token, just answer 5. The second process for reasoning is like it generates multiple tokens, like 6 tokens, and it says that adding 3 to 2 is 5, something like that. And another type of path, it is like it will segment mode. Suppose like 3 plus 1 is 4, and then 4 plus 1 is 5, and then it will generate, the answer is though is 5, 5, 5, everything is same. But the third approach, which takes 15 tokens for output, the performance is better, because if you are asking very complex question, like which needs more thinking, then the third approach performs better than the first one. So for the reasoning, there is a question, and there is a large language models, and it will generate multiple type of thoughts. So here we can see that there are 3 type of thoughts. Like first one is just answer, second one is little bit details, third one is it's little bit more details, and then it's like the third one takes more time to thinking, and it performs better. So these are three type of thought process. So large language model can generate multiple type of thought process, and then there is called a reward model. For each thought process, there are multiple reward models, and reward model can give some rewards, like some scores or something like that. And based on rewards, we will take these thought processes. Suppose like there is a third one is the best answer based on the reward model, like reward scores. So now for the reasoning, there is a very popular terms. It is called chain of thoughts. So if you are asking very complex question or multiple questions, so if you are using something zero shot or few shots prompting, then most of the time, like if the prompt is very complex, then most of the time it won't answer that good way. But if you are using chain of thought approach, it will perform a little bit better. So what is chain of thoughts? Chain of thought is, suppose the first question is, I have 10 apples, I gave 2 apples away, I ate 1, how many do I have? For the reasoning, like for the zero shot, you are just asking this question, and large language model like calculate something like that and give some answer. But for chain of thoughts, you are segmenting the question into multiple steps. Suppose like I have 10 apples. I have 10 apples. You have 10 apples. This is the one step. Then there is another step. There is another step. So you are making large language model a little bit easier, making multiple reasoning steps, and then large language model generates a little bit better answer. So your problem is, okay, this is the problem, and you are segmenting this problem into multiple steps that large language model can easily understand. This is called chain of thoughts. There is another very good term, it is called zero shot chain of thoughts. So this is a very good paper. So they showed that there is a 4 type of approach. First one is few shot. What is few shot? Few shot is Roger has 5 tennis ball and something like that. This is the example, and then you are asking another question. A juggler can judge or something like that. So based on this example, LLM generates one answer. This is called few shot. But here we can see that LLM generates like wrong answer. Few shot chain of thought is like you are providing an example, and then you are segmenting this example in a multiple steps, which is called chain of thoughts. And as you are providing examples, which is called few shot, and you are breaking this example in a multiple steps, which is chain of thoughts. That means few shot chain of thoughts, and it performs well. Zero shot chain of thoughts is like you are not providing any example. You are just asking some questions, and then it's like it still generates like a wrong answer. It's 8. It's not correct answer. What is zero shot chain of thought? It's like there is a magic line. It's called let's think step by step. So in this paper, they are not showing anything. They are saying that when they are using let's think step by step, this approach, it performs extremely well. So this approach they call zero shot chain of thoughts. It's like why zero shot? Because they are not providing any example. And chain of thoughts is like they said that LLM, okay, you are think by yourself, but you have to think step by step. So, and it performs extremely well. And this paper they shows that this performs increase 17% to 74%.
So this is only a inference time method, right?
Which one? 17%?
The zero shot COT.
Yeah.
So they didn't do anything in the training or the.
No, it's just for just for testing.
Oh.
They are not doing anything in their training.
What is the pros and cons between the few shot chain of thoughts and the zero shot chain of thoughts?
Few shot chain of thought is like it's heavily depend on your examples. Suppose for my earlier work, I provide some examples, but the performance was not good because my examples was not that good. And when I use zero shot approach, it performs well better than few shots. Because so for few shot, you have to choose very good example that LLM can go this way.
So zero shot will enable us to have a more generalization on the variety of topics or in the particular domain.
Yeah, it's like if you are not fine tuning anything, then it's like it's just only trained on the general topic. But it's like it's LLM tries to answer from the own knowledge. You are not providing any direction. Yeah.
How is the COT coded in the structure of the large language model? That's some extra layers of model, or is that a?
It's not extra layer of model. It's like just a prompt engineering. You are like they are doing something in prompt, like in few shot chain of thoughts. They are providing an example, and after they are providing this example in this way, it breaks down multiple steps. Suppose for this.
So you don't do anything in the training process. You don't do anything in the fine-tuning process. You just ask the correct question, and that's it.
Yeah.
The model is frozen. You just change the way that you ask.
Yeah. It's
so,
like.
But for other COT methods, you do enforce the model to do it in this way by using fine-tuning, right?
Fine-tuning chain of thoughts.
Yeah, I've seen some papers that you train the model with human-generated, labeled chain of thought answers, such that you can force the model to provide steps of the answers.
Okay. Yeah. This can be possible. Yeah.
But I think it goes to a previous slide.
Yeah, sure.
This, I mean, the chain of thought happens after the LLM. That means not a prompt engineering. Prompt engineering should be before the model.
This can be possible in 2 ways. The professor just mentioned that they are fine-tuning something, like using chain of thought approach. And another approach is like when you are providing the few short chain of thoughts, like examples, like steps down, break down this thing as a few short, then LLM thinks in this way. Like it can be possible for, like it can be doable for in prompt engineering and fine-tuning approach as well.
You give an example about how to break the problem
Yeah,
down.
yeah. It's like a few short chain of thoughts.
Okay.
Yeah. So Yeah. So now I'm discussing about consistency. So what is self consistency? LLM generates multiple output and select the most consistent one. So here there is a one prompt, and we are providing large language model, and large language model we are providing prompt, or we are training large language model in that way that LLM generates multiple answers, multiple path. So there is one questions. There is one question and there is answer. The first one is a few short, it's like just example, and second one is like question, actual question. And LLM generates multiple paths, and for the first path we are seeing that the answer is 18, second path answer is 26, and third path answer is 18. So now we are counting the majority vote. Which one is majority? 18 is majority, the answer is 18. So this is called a self consistency. So here, like asking a model to answer a question multiple times and picking the most frequent answer with features. So it improves the reliability. The cons is it requires multiple queries, increasing inference time. So yeah, so this is called self consistency. We are taking the majority vote.
So how long will you keep asking the same question? Like how many?
Yeah, this is the very tricky. Like how do you set the threshold? Most of the time they are providing like odd number of prompt. 3, 5, 7, but there are no perfect.
I've read a paper where they ask the same question for 1,000 times.
Yeah. Sometimes like there are no perfect threshold for. It varies.
Feedback given like okay the answer is correct or not?
Sorry.
Is the feedback given to the LLM the answer is correct or anything?
No.
Nothing.
Nothing. We are just counting majority vote. So now there is little bit advanced topics, then chain of thoughts, which is called tree of thoughts. So there are multiple type of the left one. It is just zero shot. It's like there is a input and then LLM generates some output. This is zero shot. The second example, the figure. This is chain of thought prompts. It's like input and then breaks down the prompts or question in a multiple steps, and then we are getting output, which is chain of thoughts. The third figure is self-consistency with chain of thoughts, which is self-consistency means this input goes into multiple ways, multiple directions, and then we are asking multiple times, and then we are counting the majority vote, which is called self-consistency. Now we are talking about tree of thoughts. What is tree of thoughts? Tree of thoughts is like there is multiple, like first there is input, and then input goes into multiple branch, and each branch creates multiple branch. It's not like that in chain of thoughts. It's like just a linear, like each branch does not create multiple branch. It's like each one is questioned by multiple times, but in tree of thoughts each branch creates multiple branch, and then we are taking the like which is optimal path we are taking. So the definition is an extension of chain of thoughts where multiple reasoning paths are explored. Example is multiple possible way, expand each. There are multiple way, and each one we are expanding. Evaluate which approach is best and choose best one with scoring mechanism. There should be one scoring mechanism. The process provides flexibility in decision making, but cons is it's little bit expensive computationally. So there is one example for tree of thoughts. There is one question like a farmer has 20 apples, and he sells half, gives 3, and something like that. So at the very first there are two type of paths created. First one is farmers sells half and then sells half, and second thought is farmer gives 3, and then for each thought there are multiple 2 subpaths, and then it takes from the scoring mechanism it takes the optimal one. So now
On the
yeah,
tree of thoughts,
sure.
is the prompt such that you're asking for just the first step and then you ask for the second step, or is it just give me the solution and you only take the first step from the chain of thoughts and then you feed it back in, right? I assume you have to call the model multiple times, right?
Yeah.
So you're feeding back in the result of the first prompt, but are you only after the first step? Are you only asking the model for the first step, or do you ask it for the full solution? I imagine you would just ask for the first step, but I didn't know if that biased things in some way.
Yeah. I'm not sure actually.
Okay.
Okay. Yeah. So now this is now the next approach is graph of thoughts. So what's the difference between tree of thoughts and graph of thoughts? The good thing for graph of thoughts is we can see that the like darker green one, those are the aggregate the chains. So for the tree of thoughts, it's like just expanding. Suppose we can think about binary tree or something like that. For each node, we are expanding. But for tree of thoughts, here, they are not aggregating the thoughts. But for graph of thoughts, it's like it's aggregating the thoughts and aggregating the chains. So they are how graph works is like there are multiple nodes and multiple edges. So each node thinks about thoughts, and then edges is the thought process, and then there is some nodes they are aggregating the multiple thoughts from the previous layer. So this is the better approach than tree of thoughts. So the definition is it expands tree of thoughts by structuring reasoning as a graph. Multiple ideas node can connect and influence each other. Multiple pathways merge solution and revisit previous ideas. The example is node is the partial solution and edge is dependency between the thoughts. The pros is it can handle complex multi-hop reasoning tasks, and the cons is it's little bit computationally expensive.
So in the graph of thoughts, each and every link has a particular weight to it, saying that this particular end or this particular answer is very good, or maybe it has more confidence rate, and so that we can consider that instead of all of this, right?
Each
Link has a particular confidence code to it.
particular
Like,
confidence.
for example, we
Okay.
are breaking down each and as a large question into chunks, right?
Yeah.
The first chunk is answered in the first layer.
Yeah.
So after in that first layer, it has a multiple answers to it. Like for example,
Yeah.
what is the 5 minus 10?
Okay.
Let's just say the one says it's -5, another says it's -3, and another says it's -2 or something.
Okay.
So which one has more confidence rate here?
Okay.
The
You are
minus
saying
five
that for the
plus-
each edge there should be weight or something.
Yeah. If they did not do it, maybe we can try it.
I'm not sure actually.
Here, though, right? The point is that you have -5 and -1 both feeding into a new answer, which so in this case it doesn't really help when you have something that's straightforward.
Because they're
It'd be more like, what should I try first? And you're like, well, I'm going to try to look behind the sofa, or I'm going to try to look behind the chair. And then you combine those in some way, say, oh, you should look behind something, sort of. Like,
Yeah, but all nodes are not connected to each and every node. Not
One
each and every
way.
node is connected.
Yeah, sure.
I have to answer. I think I have
Okay.
this answer. Sometimes the model itself has been used to evaluate the responses. The model can decide each response how much they are accurate, and based on those parameters, they decided to merge. And sometimes based on what cost information, they just follow the flowchart that have been drawn.
And to answer Professor Wood's answer, I think I saw a prompt in their paper. It says that you are 3 experts, and you define the first step and share it with them. And then if you're wrong, you just leave. So that's how it goes through. So that's
okay. Okay, that would make
Okay.
Like a fully connected. Each and
Yeah,
every
like steps on it.
Okay.
You
So
would you would eliminate some of the links
Yeah, like
as
if
you go
you're
along,
wrong,
right?
the expert leaves.
Yeah.
yeah. So this is graph of thoughts. So there are some difference between like chain of thoughts, tree of thoughts, and graph of thoughts. First is chain of thought is linear, tree of thoughts is a hierarchical tree, and graph of thought is network graph. Chain of thought has one reasoning path. It's used in basic simple logic, math, or question answering. Tree of thought is a multiple decision, but graph of thought is like it connects, revisit, or merge the thoughts. But in tree of thoughts, they are not merging anything. For the tree of thoughts, it's used multi-step planning, strategy games. Graph of thoughts, it's used complex reasoning problem, solve when there are dependency between other thoughts. So now I'll be describing a little bit about reinforcement learning. So in it is ChatGPT or those stuff, they are using the term called RLHF, which is called reinforcement learning from human feedback. What is this? Is like there is a prompt in left, and then there is a question in this prompt, and this question asks to LLM, and LLM generates some output, and then based on this output, we are using one human here. human figure, and human said that which output is better. Like human ranked those output, and then based on this feedback from human, we are fine tuning another reward model, and then we are using this reward model for the scoring mechanism and something like that. But the problem for RLHF is like there should be some bias from human, and using human is little bit costly. So there is another term which is nowadays very famous, which is called RLAIF. Instead of human, we are using AI as a feedback. So here instead of in RLAIF, this human will be replaced by the AI. So AI will generate some some ranked output, and based on this ranked output from AI, we are training another reward model.
The AI model can also have the bias, right?
Yeah. Everything has problem. Yeah. So we know the Cohere. So Cohere is using RLAIF. So they are. Yeah. So now I'm little bit visiting about the DeepSeek. So DeepSeek has two versions. One is R10, and there another is I think R11 or something like that. So what is model? This model run by itself that the longer and more complex the reasoning process. During reinforcement learning, two specific rule-based rewards were created. The first one is accuracy rewards the answer by testing it out. The format is like something thinking and answer tag. So in the system prompt, we can see that use think for reasoning. This is the prompt format. Use answer for reasoning, and there is a user prompt like suppose lead code problems, and then they are sending this in DeepSeek model, and then based on this format, the reasoning and answer, there is some score, and based on this score, this is the RL, and then it will be iteratively update the base model, and then finally we got the DeepSeek R10 model. But this model have some problems, so they are providing another update model, DeepSeek R1. I'm not describing the update model here. So this is the fundamental DeepSeek. Now I'm talking about scaling laws. So what is scaling laws? It's like if we improve the competing things, the performance normally most of the time it will improve. So the model scale correlates with the model performance. So there are some very popular scaling laws, which is Kaplan and Chinchilla. So this is called scaling laws. So there is for the scaling law, we can increase the computational cost. Something like we can improve the number of parameters in model. We can take the large number of data set which is so many tokens. We can improve the number of flops. So we can improve those things. Then most of the time the performance will increase. The LLM performance will increase. So now I'm talking about fine tuning. What is fine tuning? Fine tuning is we are taking the pre-trained model, and then we are trained this pre-trained model with a particular data. For like suppose we want to work with LLM in a healthcare or something special domain. So we are taking some data set from the healthcare domain, and we are training the actual model of this healthcare data that we can answer some good responses in terms of healthcare data. So this is called fine-tuning. But the problem of fine-tuning is like it's little bit computationally expensive. So how we can overcome those type of computational cost? There are some approaches we can use to overcome this computational cost. First is prompt tuning. Another is there is good approach which is called LoRa and QLoRa. We can use those approach in fine tuning to improve the to reduce the computational cost when we are doing fine tuning. So what is prompt tuning? So to overcome the computational cost, we can optimize the input prompts to steer model responses without changing weights, unlike fine tuning. So it's called PEFT, parameter efficient fine tuning technique. It's learn optimizable prompt embedding instead of modifying model's weight. So here we are not modifying model's weight. We are learn optimizable prompt embedding, and then we keeps the model frozen. Only optimize set of parameter. Set of learnable prompt tokens and added to its model input. So here we are we are we are learning from optimizable prompt embedding, and then we are using in model input. So there are some prompts. There is the good thing is it's lightweight, flexible, but the cons is its results can be inconsistent across tasks. So for the fine tuning, if we want to do fine tuning from the scratch, it will be so expensive. So we can use LoRa. LoRa means low rank adaptation. So how LoRa works is like, at first we freeze the LLM weights and we introduce small trainable low rank matrices, like there are unit vectors. There are 2 unit vectors. We can multiply both of them and we can add to the freeze LLM weights to improve the to fine tuning the actual model. So using LoRa approach, we need less number of computational costs like GPU and stuffs. And there is another approach, is called QLoRa. QLoRa is it's on top of LoRa, but it's 4-bit quantization, and it will reduce more GPU cost. So using those approach, we can do fine tuning with lower computational cost.
You mean when we do the fine tuning to the model, we have a LoRa, right? For example, the unit vector combined, it has a matrix with the padding stuff and stuff, where whatever the model outputs is directly going into the LoRa, and then we are getting another output, right?
Model output goes to LoRa? No. So basically, there is a 2 unit matrix. So LoRa, like suppose A and B. So we have to fix the what is called I forgot the name.
The matrix.
Rank. We have to fix the rank. Yes. So suppose there is a 1 by 3. That means rank is 3, and another is 3 by 1. So both are row matrix and column matrix, and we have to multiply both of them, and the value will be assigned with random Gaussian distribution, and then we'll multiply both of them, and then we'll add the actual frozen and this way this one will affect the whole model. So this is like another good approach. Like we are not using the actual model, but we are doing something else, but it will affect the actual one.
So are we just adding another layer, or we are adding into the model's weights?
Yeah, we are adding model's weights.
Which part of the weight you should add that trainable low rank matrices into the attention layer? Which attention layer? All of the attention layers, or a few attention layers?
The frozen one. So suppose there is model and we have frozen weights. We are adding those extra row matrix and column matrix into the frozen one.
It's some layers after the whole frozen one.
Yeah, layers after.
Okay.
That might depend on the way that we train the model. We can think that first 16 layers or some layers can be frozen, and then
So another very good approach is called flash attention. So flash attention is we know the vanilla LLM, like the transformer is O(n) square, which is quadratic. Quadratic means when we are multiplying key vector, query vector, it's a nested loop. So flash attention overcome this problem and converted to this computational cost to O(n), so it's like a linear. So how flash attention works? So this is a very good paper, and I'm just like describing little bit. So the first one is flash attention split the query key and value into blocks, like multiple chunks, and then it will compute the each block, each small chunk, and which can fits in SRAM. So SRAM is faster than DRAM. DRAM is using for vanilla attention or vanilla transformer, but they are using SRAM, which is more faster, and they are doing computational stuffs. Like SRAM is small, so they are in computational things in a chunk basis, and then they recompute the softmax locally, and then they are does not store the full attention matrix, and then store only the final outputs. So using this approach, the flash attention, the performances increases, and the computational cost converted to a O(n) square to O(n). So the process is speed up the training and inference LLMs. The cons is we need the hardware architecture. So earlier we talked about the tree of thoughts. So we can use tree of thoughts for sparse attention or KV cache optimization. So there is another approach, very good approach, is called KV cache. We can use KV cache optimization to reduce the computational cost of transformer O(n) square.
And here is the length of the number of tokens.
Which one?
And the big O square of n. N is
Okay. Number of tokens. So basically QKB, query multiplied by key, right? Okay. So QKB. So number of tokens in query and key, I think so.
the number of
QK transpose B. So
feature dimension for one data.
sorry.
Data, it's something that's a level of 5, 1, 2 or something. That's feature dimension.
Feature dimension of what? Query?
The input data or the number of data.
Okay. So suppose there is one input text, right? So now the query text will be multiplied by key,
Yes.
right? So that means number of tokens for query, it's suppose like n, yeah, QK transpose B. I have to revisit the paper again.
By the way, have
Yeah.
you seen the recent paper on the native sparse attention proposed by DeepSeek team?
I saw the title. I did not go through the paper. I heard that they are using the
Now
sparse.
It's very popular.
Yeah, they are using more sparse metrics. Like, yeah, that's why they are like more reduce the computational cost. Yeah. So another good thing of LLM is LLM as a judge. So we can use LLM as a judge, like we can do various type of evaluation using LLM. So there is a one demonstration which is there is some benchmark data. They have input and output which is like level data, and we are using a prompt, particular prompt, and then LLM generates some suggested output, like the predicted output. Okay, the label should be something, or LLM can generate some text, and then we are using this benchmark data, like we are correct this output, and this suggested output and correct output goes to LLM and asks LLM, okay, which one is better, or you can rank them, or you can score out of 10 or something like that, and LLM generates some scores or some answer or some decision, and we are providing some human expert, and human expert evaluate how LLM good it is, and then like human expert, we are taking the judge performance, and then we are updating the LLM as a judge. So this is like we can do like LLM as a judge using human experts. So there are multiple things we can do for LLM as an expert. First one is there is two type of response. Like one is reference, which is ground truth, and another is new response, and we can ask LLM, okay, do you think both are similar or not, like just a binary question, and LLM says that yes or no, something like that. This is one type of using LLM as a judge. Another is there are multiple type of text, and we can ask LLM, was the user requested resolved, or there are some criteria. Based on this criteria, LLM says that like just binary response, yes or no or something. Or it can be evaluation by criteria. It's like there is one response, and evaluate if this response is awesome. So it's like just binary. If LLM thinks that this is awesome, says awesome, other is not awesome. So it's better if you do something binary classification by LLM rather than the multi-class classification. We can do also pairwise comparison. Like there are two type of response. LLM can say that which one is better and why this is better.
Are there effective ways to make this robust framework, LLM as a judge?
Yeah, so I read couple of papers. So most of them they are doing some fine tuning. So they are taking some data. Maybe they are using some annotator or something like that, and they are taking some data and they fine tune Llama model, and they use this fine tune model LLM as a judge to do a good task. Yeah, like instead of zero shot prompting, they are fine tuning their model. Yeah.
And for Professor Kaur's question, yeah, the n square means both the query and the val key. are combined here is called as N square.
Yeah. So, but we saw so many things in LLM, but there are some problems in LLM still exist. First of is the LLM is a black box. It's like the lack of explainability. So black box nature of models make it hard to understand decision making process. So we can do something like explainable AI, which is more interpretable. And suppose like attention mechanism and saliency map. What is this? Attention mechanism focus the important words. Saliency map is focus the important key things. Like suppose in a figure there are some key stuffs, saliency map figure the key stuffs. So we can do something little bit explainable that that remove the black box nature. Another is there are some bias and fairness issues from LLM. Like we are training some data, we are training the large language model, but LLM can LLM can get the bias from this training data, or may or generate some leading or harmful outputs. So it's heavily depend on which type of data we are using to train our LLM. So we can use debiasing technique or diverse type of data set to overcome these bias and fairness issues. Another most important thing is high computational cost. We know that GPU is very costly. So if you want to fine tune model, or if you want to do something with LLM, then it's very costly. So also if you want to do some prompt engineering also, the API, like GPT-4 has some API cost or something like that. So there are good approaches like suppose sparse model quantization, and there is called SSM. SSM is solid state space model. There is a very famous paper called Mamba. They are using this approach to overcome this computational cost, and we can use flash attention or KV cache approach. Another problem of LLM is LLM still struggles when there is text is long term. Like if their text is very long, then LLM still struggles. So the proposed solution should be incorporate memory mechanism or hierarchical attention, or we can use Retrieval-Augmented Generation (RAG). I'll describe a little bit later. And the right figure, it's a just scaling thing. It's like there is a, I think, computational cost increase over the years. Like the larger model comes and it needs more computational resources and stuffs. So there is another method, is called Transformer XL. So it's little bit better than vanilla transformer. So vanilla transformer has fixed length segments, suppose like 512 tokens or something like that. What is Transformer XL? Transformer XL takes the output from the previous segment and then use this output from use this in current segment. Like take the output from previous segment and put into current segment. Or to overcome the problem, we can use Retrieval-Augmented Generation. So there is bunch of common problems that still exist in LLM. First one is LLM still heavily rely on parametric knowledge. It means LLM can generate whatever he has in whatever it has in parameters. Like it can't generate something else. Or if there are something very nuanced or niche topic, then LLM struggles. Most of the time LLM generates a very generic answer, or sometimes LLM can't cite or wrong citation. Like if you ask something like that, it can give the wrong citations. And sometimes it's verbose response, like the text is not, or some biased response. So all of this problem we can overcome using Retrieval-Augmented Generation. So yeah, so or some other approaches as well, like we can use layer-wise relevance propagation, shape values, like it's a explainable AI. We can do some improving contextual understanding, or some model pruning, knowledge distillation. Knowledge distillation is like train a small student model from the big teacher model. Or earlier I talked about the LoRa, lower rank adaptation. We can do those type of things to overcome the problems. So now, to overcome this type of problems, like we want to generate some better response for LLM for the niche topic or very updated topics. So we can integrated RAG, Retrieval-Augmented Generation, to LLM to get a better response. So what is RAG? So reg is, there is a question and there should be one retriever, and we are asking something like who is the president of the United States or something like that, and retriever take this question, and then retriever takes some more information from additional context, which is maybe additional vector database. Retriever collects some information from additional vector database, and there are actual input. Retriever concatenate both and send to LLM, and LLM generates better response. So this is called retrieval-augmented generation. So there are two things in reg. First one is retrieval, second one is augmented. What is retrieval? Retrieval means this retriever collects some information, retrieves some information from context. This is called retrieval. What is augmented? Augmented means retriever gets some prompt from question, and it also retrieves some information from context, and this retriever augmented both of them and sent to LLM, and LLM generates better response. So this is called reg. And now how reg overcome those type of problems? So reg augments external knowledge. So if there are some very niche topics, something about healthcare, we assume that maybe LLM perform does not well. So reg maybe performs well here. Also it retrieves relevant passages to provide additional context for long contextual tasks. Earlier we saw that if the sentence is very big or long, LLM performance is not good. So for long context, reg performs well. It can provide citation, user can verify. It overcomes the generic answer or verbose answer. Reg can provide little bit precise answer, and it extracts specific information to overcome poor performance on niche topics. It encourages to generate concise answers. But there are some problems still exist in reg, and now researchers are working on how we can retrieve the actual correct information from the external vector database. So what is the problem of vanilla reg or traditional reg? Traditional reg retrieves information for a fixed number of passages. So here in this example you can see that this is the context. So this context is a vector database. There should be multiple chunks, and retriever collects those information from those chunks. So every time you have to mention that, okay, I need 3 chunks to collect information or 5 chunks. It's like a fixed number. So this is the problem. Another problem is, suppose we collected some information from retriever, but we have to check that this retrieved information may align with LLM output or not. Sometimes it contradicts or something like that, then it deteriorates the LLM performance. So we have to check that. So there are some problems still exist in reg, and people are working on it. So first one is, there is a very good paper, it's called self-reg. So they try to solve some problems, which is, so to introduce this problem, they introduce the self-reg. So self-reg trains to LLM to adaptively retrieve relevant passage. So here they are saying that not fixed top K. That means in this context, there are some fixed number of chunks, suppose like 3. Retriever collects 3 number of chunks. That's the problem, because it should be varies on prompt. Like suppose you are providing different prompt, there should be maybe 5 chunks. We need 5 chunks, or we don't need any information or anything. So they are saying that not fixed top K. They are not providing fixed top K, and they are using 2 type of tokens. One is special tokens, and another is reflection tokens. For the reflection tokens, they are using retrieve tokens and critic tokens. So what is retrieve tokens? Retrieve token is they are using retrieve when it's necessary. So here for retriever collects the information from context. So sometimes for particular prompts we don't need any information from the external vector database. What we should do? We are stopping collect information from the context. We are saying that, okay, this prompt goes to direct to LLM. This is retrieve. This can do retrieve tokens. It's like when retrieve is necessary, retrieval tokens do this thing. Another is critic tokens. Critic tokens is it's evaluate quality and factual accuracy of LLM generation. So yeah, we can see that this is the example. So there is a 2 type of figures. The left one is a vanilla reg. What is vanilla reg? Like the normal reg. There is a first prompt. How did US states get their name, and they are retrievable. Like there are 3 information. We got like 3 documents from the external vector database, and all of the documents goes to LLM alongside the prompt and then generate some answers. But we can see that there is some red signs, that means there are some contradict answer or misinformation or wrong answer. So the right side is their proposed approach. What they did, it's like, at first the question is how did US states get their names, and the first one is retrieve on demand. That means they retrieve whatever they needs. Suppose like there are some prompt they don't need any retrieve, they don't retrieve. So then suppose there are three type of retrieval done, and then for each retrieval they took the actual prompt and there are some answers, and there are critic token. Critic token, they are using LLM, another LLM for critic token, and judge which one is better. So there is 3 response, 1, 2, 3, and they said that 1 is better than 3 and 2. So they took the 1, and they don't take 2 because 2 is like less. Like based on critic token, 2 is not good. So they take 1, 3, and then generates better answer. So this is their approach. So the process is they call on-demand retrieval. LLM decides whether to retrieve passage on the input and generates a retrieval token if needed. If retrieval token needed, it generates, otherwise not. Another is passage evaluation. If retrieval occurs, LLM process multiple retrieve passage, evaluate their relevance, and generate stacks output. What is this? This is like there are multiple type of tokens, multiple type of output we got from the retrieval, but there are something misinformation or something else. Critic token decide that okay, which one we need, which one we don't. And LLM generates critic tokens to assess the quality of its output and select the best one based on factuality and overall quality. LLM trained to generate text interleaved with reflection tokens. Critic model, they are using GPT-4 here. So this is like pretty much the high level overview of self-reg. This is a very popular paper in reg. So I will be describing another paper here. It's called afterward. The title is Overcoming Imperfect Retrieval Augmentation Knowledge Conflicts for Large Language Models. So they are more focusing on knowledge conflicts. So what is knowledge conflict? Knowledge conflict is sometimes LLM and reg disagree. LLM said something like 1, reg says 0, like both are disagree. So they are trying to solve this problem. So they are saying that 2 things. One is internal knowledge, another is external knowledge. What is internal knowledge? LLM already knows from training. From the training, LLM says, okay, I know this thing. What is external knowledge? LLM retrieves some information from external sources, suppose reg. This is called external knowledge. The problem is when LLM use bad information. What is bad information? It's like the retriever collects some information from vector database, but this is something noisy or something else, then LLM like it deteriorates the LLM performance. So they are trying to solve this problem here. So when conflict happens, it means LLM internal knowledge, what already knew LLM, and then the information from the external database, they are conflicting. So they are providing this approach afterward. So before using external information, third-party information, they ask LLM, like just LLM, no third-party connection. They said that what do you know already about this, and then use this information as internal knowledge, like LLM already knew this thing, and then they collect some information from reg, and then they said that whether both are disagree or not. So afterward combines the LLM's internal knowledge with the retrievable external information. It carefully checks for conflicts between the 2 sources and decide which one is more reliable, whether LLM is more reliable or reg information is more reliable. If the retrievable information is irrelevant or missing, afterward ignores it and relies on the LLM internal knowledge. So their primary focus is they don't deteriorate the LLM performance. So if they thinks that like the afterward thinks that the information from third party is not good, they relies on only LLM internal knowledge. So if the retrievable information is useful, it integrates with LLM knowledge to generate a better answer. So if like the reg which is not good, then it still exists, performs, like it does not deteriorate the LLM performance. So that's the main concern of this paper. Even if the retrieval information is wrong, AstroDrake can fall back on the LLM's internal knowledge. If the information from third party is not good, they just rely on the LLM performance. It intelligently combines internal and external knowledge, resolving conflicts and filtering out the bad information. In the worst case scenario, where all retrieved information is useless, suppose we are providing one third party vector database and which is very noisy, AstroDrake still performs well. It still performs well as same as the LLM. Like they are not taking the noisy data from the LLM, from the RAG. So this is the figure. It's like the 45% is like LLM and RAG both are disagrees. There are some true positive and false positive. Also, like sometimes RAG disagree, or sometimes like RAG incorrect, sometimes LLM incorrect. When they are both are incorrect, they are said that both sides are wrong. It's hard to improve, but combining internal external knowledge may help. Okay, so there is last paper, what is improving factuality with explicit working memory. So earlier we saw that there are some self-reg, which is they are using the iteratively retrieving and verifying the information. But the problem is this like earlier self-reg, those are restricted to a single retrievable steps and it lack dynamic feedback integration. The first one we saw that there is using the critic tokens for judging that which one is better or something like that, but they are not integrating the dynamic feedback integration. So in this work, they are using a external feedback, which is called fact-checking feedback. To like after retrieving the information, they are using external sources to check whether those information is good or not. So this is they call explicit memory. So there is 3 key features of this paper. First one is real-time feedback. So memory is updated based on online fact-checking and retrieval feedback. So they are using online fact-checking, like some external sources, not like critic token from GPT or something like that. It's not like that. They are using online fact-checking and error correction. What is error correction? It can backtrack and correct false claims during generation. So LLM generates something. If the generation is not good, it can backtrack. Another is flexible memory units. Memory can be updated, appended or deleted based on relevance. So they are using the third party source. If they said that this retrievable information is not good, memory can be updated, like deleted the false information. So in AWS architecture, first one is memory initialization. Memory is filled with latent representation of retrieved passage relevant to the input prompt. First one is like latent representation of retrieved passage. And then the main thing of this paper is dynamic memory updates. So they are using fact-checking feedback. If a generated statement is incorrect, memory is refreshed with correct information. And another is retrieval feedback. Newly retrieved documents are added to memory if needed. And they are using KV cache approach, which is a parallel thing for efficient update and reuse. So here we can see that there is like there is prompt is what can you tell me about bird of paradise flower or something like that, and there are some multiple information from the multiple chunks, and they are using fact-checking feedback, and based on fact-checking feedback they found okay those are the information is not aligned with the external sources. They are updating the memory and then they do it. So the integration of this work is they are using fact-checking feedback, which is fact-check with external sources and then update the memory. So okay, so this is the paper, and there are some feature directions researchers are working on it. First one is they are integrating RL like RLAIF or RLHF with LLM to improve the performance. Another is they are working on the trade-off between open LLM and closed LLM regarding share words. Suppose like ChatGPT, they are not sharing their words, or Llama, they are sharing their words. So that should be one trade-off. Like if you are using a closed LLM, then suppose you are using API and you are sharing your own maybe protected or private data. So, or if you are using open LLM like Llama, many people can do bad thing, like install the whole open LLM their own system, and they are doing something bad purposes. So they are working on it. And scalable and sustainable AI. So focus on creating models that both are powerful and environmental friendly. So like using a like making a foundational model is very costly or something. So researchers are working on student teacher model, like 10-day student model is small model from the bigger teacher model, or they are doing some pruning or quantization or sparsity approach to make less computational cost. And also they are using this external vector database like Retrieval-Augmented Generation to improve the LLM performance. Yeah. Any questions?